So we visit resonance one more time. And in fact, we learned resonance is partly because of this. So the resonance effect actually helps stabilize the conjugate base, resulting in stronger acids. And it's the reason behind it is really simple. Again, is because it delocalizes the negative charge slash the electron density. So I always like to think of resonance as, there's this person carrying this heavy, bag full of money, whatever that is, um, only in one hand and on shoulder versus kind of like, dividing it into two and it's easier to carry. I guess you can think of it that way. May work actually, may not work this analogy, but that's the idea is you spread it rather than carrying one bag, from the grocery store, huge with everything in it and barely moving it. You actually divide it into two bags and you move uh, again, much easier. So let's look at these two examples. So the pKa of, once again, this is an alcohol, would be around 16. The pKa of carboxylic acid would be around 4.8. So we know that this is a stronger acid. So let's look at the conjugate bases. The conjugate base of this one is CH3, CH2, O minus. And if I were to actually draw it even more, I'll keep the CH3 the same. I'm just going to draw this right here. Right here. And let's draw this one. We can keep the CH3, but it's obviously right there. Right there. So then you ask yourself, what makes this any different? Well, we have resonance here. Remember, we spent a lot of time last week is that we can move one of these lone pairs, breaks its pi bond. And what's happening here is, what's happening here is that you're forming this resonance structure. Right. So what is happening here is that notice that the negative charge is not staying in one place or on one atom. So what is happening is that it is spreading the negative charge. It's delocalizing it. It's moving it around and not keeping it in one place. So here we say that the negative charge is delocalized or spread out over two oxygen atoms. So obviously that's going to result in less basic, which means it's more acidic conjugate. If it's less basic conjugate base, then it's a more acidic acid or the stronger acid. So this is really what resonance is. So look for resonance as a stabilizing force. And while we're here, so you can actually look at it right here. If you look at this electrostatic diagram, right, map of electron density, you notice that rather than keeping this, red means electron density, high electron density. That's what red means. Look how it's actually spread out over two atoms here, making the anion more stable. Now, the hybridization effect is a last one that we will examine. And in this case, let's just move it around here. So what is happening in the hybridization effect? What's happening is that if you look at the conjugate bases of ethane, this is sp3 hybridized carbon, versus ethylene, the conjugate base, this is sp2, and this is sp. Again, we count, remember with hybridization, we count the number of electron domains. We have 1, 2, 3, and 4, so that's sp3. For sp2, we have 1, 2, and 3. So again, 1, 2, and 3. There's a lone pair, a double bond, and a single bond. And then if we have the lone pair and the triple bond, that's only 2. So that results in an sp. So why is that? What's happening here? Well, this one has an S character of about 25%. So where did that come from? Well, if we have S and 3 P's, and this would be 25%, 25, 25, 25, and that adds up to 100. Of course, this would be a 33% because, again, you only have an S and 2 P's, so that's only 1/3. And of course, this would be 50% because you have S and P, so that's 50, 50. So what's happening here? Why does 1, for example, result in the stability? Well, you can think of it this way. So the carbon atom is more electronegative than H. And what happens here is that if you actually have if it's in an SP, right, it means that you actually have more of this electron density if it's 50% in the S, and that would be closer to the C. So again, S we would say here, and more S character, like I said here, we're down here. Actually, it's down here, is closer to the nucleus. In effect, C with more S character is more electronegative. Electrons are pulled toward the nucleus and they are lower in energy. So what you need to do is you need to remember that the more S character you have, the stronger the acid will be. The stronger the acid will be. So these, in fact, if we look at the pKa's of some of these, like the pKa of acetylene right here, this would be about 25. For ethylene, it would be around 44. And for ethane, it would be about 50. Once again, this has more S character than, of course, the one with sp3.